This is where we actually start to get enough mathematical functions that allow us to determine how many electrons and holes are available, which we need to know when we get to the point where we start creating semiconductors for a particular reason. We are not going to be able to do this yet, determine the number of carriers, but we're going to get close. And after the next test, we'll actually put this stuff together and determine how many electrons and holes there are in a particular compound. So first of all, if we need or want to know how a semiconductor works, we have to know how many charge carriers there are. We have to have some idea of how many electrons there are and how many holes there are. And depending on the type of material, we might have the equal numbers, we might have more electrons, we might have more holes, we might have an incredible number of electrons and very, very few holes, or vice versa. And all of those go into determining how semiconductors work. So we need to know that. So we're going to start out by figuring out how many available slots for electrons or holes there might be. So that's the first thing we do. This is something known as the density of energy states. We talked about kind of figuring out the number of states that are available, and we just need to know what the density is and how many states are available in, like, per cubic centimeter in a particular compound. So we need to know basically how many slots are there that we can put electrons into. Once we know that, then we can combine that with the probability of finding a particle in that slot, and then we can combine it and determine basically how many there probably are. So we're going to talk today just about how to figure out how many states there are, and how to figure out the probability of certain states being occupied at certain energy levels. And then after the next test, or the coming test, then we will actually put those together and be able to determine the number of electrons or holes in a particular type of material. So the density of states function tells us the total number of quantum states between two energy levels, whatever they may be. So we have two energy levels we've been dealing with. We've been dealing with the conduction band, conduction energy, and the valence energy, and then we talked a little bit about the energy kind of in between, not a whole lot. Sometimes I forget because I'm typing up slides and I'll think we've done something, and it's like, no, I remade the PowerPoint, but I didn't actually talk about that yet. So in the conduction band, we can figure out the number of states between an energy that we know and the lowest energy in the conduction band. And we can figure out that value by this particular function. Note that all of these are constants except E and EC. But we don't know what EC is, so usually we just determine the difference between the two. So we don't actually ever know what the value of the conduction energy is, and we don't know the value of the energy, but we know how far we are from that. So we know how much more energy we have than, say, the conducting energy. We know the difference between them. You'll notice that the effective mass of the electron is used here because we're actually inside a crystal. And this is just a function that gives us the number of states between these particular values. We can do the same thing with holes in the valence band. We can actually find the number of quantum states in the valence band between the valence, and the valence energy is actually the highest energy in the valence band, and lower. We can find the number of states in there. The only difference is we use the effective mass of a hole instead of the effective mass of an electron. But both of those would allow us, if we know the difference between, to determine the number of states that are available. There is also an area between the highest energy in the valence band and the lowest energy in the conduction band, and that is the forbidden area. And there are no states available there. So between the conduction and the valence band, there are no energy states at all. And if you were to go use either one of those formulas and have values in that forbidden area, there is no particular states that are available, so nothing can actually be in that area. That just energy-wise is not possible. So we can graph these. These are relatively simple to graph. And what we can do is sort of look at them. We've sort of drawn this before where we had the valence energy at a particular level and the conduction energy at the particular level. And basically, as the energy goes up, the function increases either into the conduction band or down into the valence band, depending on what's going on. So basically, for more energy, you get more states. If we want to find the number, we can integrate. Are we going to integrate? Yeah, we're going to integrate. This is one of the times when we're going to do an integral. And I would highly suggest that when you come to the point where you write a formula sheet, write down what the integral of this function is rather than trying to do the integral. I mean, you can, but you don't have to. So we're going to find the number of quantum states in silicon for an electron per cubic centimeter, and we know what the energies are. We just know, we don't even know what the conduction energy is. We just know that the energy is between the conduction energy and then conduction energy plus K times T, and that's just one of those common things. That's basically a unit of joule in joules. And we're just going to figure out what that value is. So what we're going to have to do is we're going to have to integrate from the conduction energy to the conduction energy plus KT. And then we will have this function, GC of E dE. And the nice thing is, first of all, there's a whole bunch of stuff that's constants. And constants don't get integrated, so I'm going to put them outside the integration. And you'll notice that on the inside, it's not terribly complicated. But I am going to, rather than put the square root, I'm going to do E minus EC to the 1/2 dE, just to make it a little easier. Yeah, it's really not that bad once you get to that point. So this means that the number of states is 4 times pi times 2mn star to the 3/2 over h cubed. And then in order to integrate and make it come out right, we have to have a 2/3 here because the function on the inside is going to be up to the 3/2. And we're going to get E minus EC to the 3/2 here. And we're going to evaluate this from EC to EC plus KT. Hopefully I won't run out of room, but I might. Let's see. And the nice thing about this is that a lot of stuff cancels, which is nice. So I'll write out my constants again, and my 2/3. And then, in order to evaluate this, I've got EC plus KT minus EC to the 3/2 minus EC minus EC to the 3/2, which is good because a lot of stuff's going to cancel. basically we've got these cancel, and so we end up with 4 pi times 2 effective mass over h cubed times 2/3 times kt to the 3/2. And I may run out of room trying to write all these numbers in. This is where your calculator can either be your worst enemy or your best friend, because this is exactly like what we were calculating when we did the first participation problem. If you did the first participation problem and were getting errors or zeros for your answers, you just need to come up with a way of doing these calculations in parts. Don't try to overwhelm your calculator by putting too much in. So we're going to have 4 pi, and we have 2, and then we have the effective mass is 1.08 times the actual mass. So we have to put 9.11 times 10 to the minus 31 kilograms, which is how much an electron weighs. So that's one of the pitfalls that happens sometimes. Students will write in the effective mass and not actually write the actual mass, and then you end up with a really, really, really weird number. So all that stuff is to the 3/2, and then let's see, we have it over h, which is 6.625 times 10 to the minus 34 cubed times 2/3 times k times t. Ooh, I am running out of room. Let's see, 10 to the minus 23. What did I do?
You can also put like e to negative 23. Or e to the 14.
What did I do?
No, you're fine.
No, he's saying like you could just shorten out times 10
Yeah.
to the
Just put capital E to the 23. If you want to, shorten it up.
I don't want to.
Okay. You're the professor.
I am. Only because I want to write all these numbers down, but I'm not actually going to piecewise solve them. So let me just make myself more room here so I can write this in properly. But usually I don't run out of room so badly, but 300 K was the temperature, and that was to the 3/2 also. I don't know why my pen gets fat on the edge, but it does. Sorry. So all of that comes out to 2.12 times 10 to the 19 states per cubic centimeter. My original answer was 2.12 times 10 to the 25, but that's in square meters. And there really isn't much of a point in calculating states per square meter or cubic meter. It's been a long day. So that is basically how we figure out how many slots there are for electrons at that energy level. Not at any other level, just at that energy level. So that's half of it. This is how we can figure out how many slots there are. The other thing we need to figure out is how likely it is that there's going to be an electron available at that particular energy level. And that is determined by something known as statistical mechanics. All we do in a crystal is we basically determine the electrical characteristics and the number of electrons or holes by grouping them all in a big group and saying there's this many of them, what's the probability that they're here or here? And we have to have some kind of equation that will give us that number. So what we use is basically, there are 3 different ways you could determine this, but only one of them really works, so I'm not even going to mention the other 2. But there's 3 laws that govern large numbers of electrons that have come up over the years. But the one that we use is something known as the Fermi-Dirac distribution function. And I know that sounds very technical, but it's actually really easy. Basically, it assumes that we can't tell the difference between individual particles, And there's only one particle per quantum state. The other two statistics have different assumptions that they make, but this one is pretty close to what we actually determine. So, anytime we have a system that has a lot of energy levels, we have a way of determining, or we kind of have a name for the energy that is the highest in the system. So there's multiple energy levels that are occupied, but we call the Fermi energy, or the Fermi level, the highest energy level that's occupied. And I'll illustrate that. I'll illustrate that today, which is good, because if I did it later, you wouldn't remember what I said today. The Fermi energy doesn't necessarily equal an actual energy level. It just lies somewhere. Oftentimes it lies in the forbidden area. It's just the highest energy level that is there. It's not necessarily the energy level of anything in the system. It's just the highest energy level there is. It becomes important later. When we start putting things together, everything has its own kind of Fermi energy level, but when you slap things together, they all have to have the same Fermi energy. So there are energy adjustments that happen when we start putting things together, like metals and semiconductors, that have to allow for that energy to be the same. So that's the one energy in a system that is always going to be constant all the time. The conduction energies and the valence energies, they can actually kind of shift up and down depending on what's going on in the crystal, but the Fermi energy is always going to be constant throughout a system, throughout an entire crystal. So, the Fermi-Dirac distribution function just tells us what the probability that an allowed state is occupied based on where it is in relation to the Fermi energy. So, the Fermi energy is the highest energy in the system, and if you're at an energy lower than that, chances are really, really, really good that that state would be occupied. If the energy is higher than the Fermi energy, chances are very, very slim that that state would be occupied. That's basically what it's saying. So, also, and this is something I just need to remind you of, we usually just use differences, again, of energy levels. We don't use we don't say the Fermi energy is this many joules and the actual energy is this many. We just say they differ. And generally when we say they differ by a certain amount of electron volts, not joules. And that's just sort of a standard thing. So 1 electron volt is 1.6 times 10 to the minus 19 joules. On the bottom of the equation, you have E minus EF, which is going to probably be given in electron volts. K times T is in joules, not electron volts. So that has to change units in order to match, which means that you're basically going to have to take the KT value and divide by 1.6 times 10 to the minus 19 to put them in the same units. That is another pitfall that students tend to fall into. Is you're given an energy difference in electron volts, you calculate K times T and you get an amount of joules and just throw it in there without thinking. And K times T is in joules. And if you're going to put it in electron volts, you just have to divide by the charge of an electron. And then you will end up with the top and the bottom in electron volts, and you get a great answer. So what does this function actually tell us? Well, let's look at it when you're at 0K again. 0K is a great temperature. So if we look at that, basically, if E, or the energy level, is less than EF, that means that E minus EF, that whole exponential just turns to negative infinity, which equals 0, and the probability of finding an electron there is 1, which is what you would expect at 0. They can't go anywhere. If the energy is greater than the Fermi energy, the exponential goes to positive infinity, and the whole function equals 0. So if we graph that, what we end up with is the function equals 1, the probability of finding an electron below the Fermi energy at any energy level below the Fermi energy is going to be 1, and the probability of finding one greater than the Fermi energy is 0. That's at 0 K. As we increase the temperature, the probability of finding electrons above the Fermi energy begins to increase just a little bit. So basically, if we look at the Fermi energy and the density of states, we could kind of put them together, and we'll put them together more later. But the number of states will be the area under this curve from 0 to whatever the Fermi energy is, and that would tell you the number of states for that particular place. So that was a terrible word to think of, but I'm getting tired. Here is an illustration just to get you an idea of what the Fermi energy is, because that tends to be a difficult concept. If we had slots to put electrons in, and we had a number of slots, and we were at 0 K, all the electrons would be at the lowest state they could be, and they would just start filling them up until they got to the highest, lowest state they could have. And that would be where the Fermi energy would be. It would just be right above the highest state. If you increase the temperature, some electrons are going to start to move. And when they do, they will leave behind spaces, and other electrons will move, and the Fermi energy will move up, because now it's going to be above those upper state. It doesn't mean that every state is full below it, but it does mean that its value has gone up. So if we look at the Fermi-Dirac function, you'll notice that as the temperature increases, it starts to get more of a curve to it. You start to get a little bit of it, a little bit of probability of finding an electron above the Fermi energy, but it's still not a lot. Most of the stuff is going to be below that value. And the probability of finding an electron or a state being occupied at the Fermi energy is always going to be 1/2, no matter what the temperature is. That's just sort of the inflection point of that curve. All right. This is the other type of example we can do with this. And this is these are finally the kind of problems you might see 1 or 2 on the actual test or the homework. So, you can wake up for a minute. We want to determine the probability that an energy level 0.03 electron volts above the Fermi energy is occupied by an electron. That's what basically the Fermi-Dirac function will do. So this means that E minus EF is going to equal 0.03 electron volts. KT is going to equal Boltzmann's constant times 300, which gives you a value, again, in joules, 4.14 times 10 to the minus 21 joules. And we can't have the top of the function be in electron volts and the bottom be in joules, so we're going to divide that by 1.6 times 10 to the minus 19, and we're going to get 0.0259 electron volts. And that is actually the standard temperature. That is actually a parameter that occurs frequently in electronics courses. That's actually known as the thermal voltage. It's the voltage at room temperature, and if you've taken engineering electronics, you've already seen it. In here, we fluctuate temperature a little bit until we get to after this test, and then everything kind of stays at 300 K. So that value KT in electron volts will be 0.0259 as long as you're at 300 K. If you're not at 300 K, it's going to change a little bit. So the probability function is going to be 1 over 1 plus the exponential of E minus EF over KT, which is 1 over 1 plus exp of 0.03 over 0.0259, what I get is 1 plus 1 over exp times 1.159, which makes sense because 0.03 is just a little bit more than 0.0259, and that would give me 0.239 or 23.9%. So what does that mean? That means if you are at 300K at an energy level just slightly above the Fermi energy, there's about a 24% chance you'll actually find an electron there. Which is, reasonable. The last thing I'm going to tell you, and this is not something you're going to have to use right now, but it will come in when we start combining. We're going to actually combine the density of states and the Fermi-Dirac probability function together after the next test, and that will be able to tell us how many electrons and holes we have. But the one last thing I'm going to tell you is that you don't always have to use this whole big Fermi-Dirac thing, because this 1 over 1 plus thing, if the energy difference is much bigger than KT, so it wasn't in the situation where we just did, but if it is much larger, then we can actually take out the 1 over 1 plus and just do minus EF over KT and take the exponential of that. And when we take that function and combine it with the density of states function, it will be much easier to do it that way than to have the 1 over 1 plus, so we will use that approximation later. But if you are asked to find the values now, use the original one. The approximation works, but it only works kind of way above the Fermi level, not kind of below it. And it diverges madly from what's actually supposed to happen.